So welcome to another session of Everyday Mathematics. Here at Everyday Mathematics, as we always say, we do enjoy solving the harder problems, but above all, we also see and appreciate the beauty in the simpler problems. So today we are still on the MIT 2022 Integration B regular season, um, and we are looking at the topic of absolutes. So we extracted problem number 18 from the regular season set of questions. And I hope you do enjoy our solution to the problem. So the problem itself was the integral from x equals to -1 to x equals to 1 of the square root of 4 minus, into bracket, 1 plus the absolute value of x, close bracket, squared, minus, into bracket, square root of 3 minus square root of 4 minus x squared. So before we jump on to the solution, again, just a big shout out and a big thank you to our subscribers. We're growing. We thank you for your support. We don't take it for granted. That's why we are here. For our first-time visitors, we highly encourage you to subscribe to our channel. Here at Everyday Mathematics, we mainly just go out, pick seemingly harder problems, and we propose solutions to them. To our repeating viewers, we do encourage you to subscribe to our channel. We are here and we'll be here tomorrow. So please just pause the video for a second and press on that subscribe button. So let's go to the solution to this problem. As you can see, that absolute value kind of complicates things. But one thing that should be at the back of your mind when you look at such problems is, first of all, it's convenient to separate these problems into two separate integrals. So for me here, what I've done is I've separated the integral between this blue integral and the green integral. Now, since we know that the absolute value of x is the same as the absolute value of negative x, and also since we also know that negative x squared is the same as x squared, and we see that this integral spreads between -1 and 1, it means that for the blue integral, this is the same as twice the integral from x equals to 1 to 1 of this integral, but with the absolute value replaced by x. Why? Because the integral from -1 to 0 is the same as the integral from 0 to 1. So why do the heavy work of integrating from -1 to 0, yet we could all bunch everything within the 0 to 1 regime? So that's why we introduced twice the integral. And since the positive x is the same as the negative x for the absolute value, so we'll just keep x as x in the positive regime. And then the same thing would also apply for the x squared, since negative x would be squared is the same as positive x squared. So we could do the same thing and say, okay, this integral is the same as twice the integral of √3 minus √4 minus x squared from 0 to 1. So let's focus on the blue. When you see a square under the square root sign, the first thing that one could quickly jump to is substitute with the trigonometrical function. So since we have a 4 here, we want to make these have the same constant as 4, but also when you square it, then you can get one function that is squared, and then the square root of that would be a simple trigonometrical function. So we chose 1 plus xb equal to 2 sine theta, such that when you square 2 sine theta becomes 4 sine squared theta. So 4 minus 4 sine squared theta would be 4 cosine squared theta, and the square root of that would be 2 cosine theta. So first of all, dx d theta based on that is 2 cosine theta, and so dx is the same as twice 2 cos theta d theta. Now when x equals to 0, from here, that means 2 sine theta is equals to 1, and therefore sine theta is equals to half, and therefore theta is the same as arc sine over half, and so theta is essentially pi over 6. Now when x equals to 1, then 1 plus 1 equals to 2, and so 2 is equals to 2 sine theta, and therefore sine theta is equals to 1, and therefore theta is equals to arc sine of 1, and theta is therefore pi over 2. So the integral now is the same as, in place of 1 plus x, we put 4 sine theta, which becomes now 4 sine squared theta when you square that. And so when you pull 4 out, it becomes 2, and so 1 minus sine squared theta is cosine squared theta. Square root of cosine squared theta is cos theta. So essentially we have 2 cosine theta, which is the same as 4 cosine squared theta, with the limits substituted appropriately. And so cosine squared theta is the same as cos 2 theta plus 1 over 2. So 2 by, when you divide 4 by 2, it becomes 2. And so we have the integral of 2 times cosine 2 theta plus 1. And so the integral of cosine 2 theta is 1 over 2 sine 2 theta. And then the integral of 1 is theta. And so applying the limits appropriately, we have 2, the constant, into bracket a half sine 2, then the upper limit, pi over 2, plus in place of theta, we have pi over 2, minus a half sine 2, the lower limit, pi over 6, plus in place of theta, pi over 6. Now 2 times pi over 2 is pi, sine of pi is 0, and then so we have now pi over 2 minus sine 2 times pi over 6. This is pi over 3. Sine of pi over 3 is root 3 over 2. And so then pi over 6 remains there. So essentially now pi over 2 minus pi over 6 is the same as is the same as 2 pi over 6, and then that's pi over 6, 2 pi over 6, which is when you divide 2 pi by 6 is same as pi over 3. Now we multiply by this 2, it becomes 2 pi over 3. And then as you can see here, when we multiply 2 by half of this, it remains pi over 3, root 3 over 2. So we have minus root 3 over 2. Now the same thing applies to the green integral. The green integral here, we can let x be equal to sine 2 sine theta, so that we can factor out the 4, and then we're left with 1 minus sine squared theta. Therefore, based on this, dx d theta is 2 cosine theta, and dx is the same as 2 cos theta d theta. Now, when x equals to 0, what this means is that sine theta is 0, and therefore theta is arc sine of 0. Therefore, the lower limit is 0. And when x equals to 1, theta equals to arc sine of 1 over 2, and therefore theta is equals to pi over 6. So therefore this integral is now root 3, in bracket root 3 minus square root of 4 minus 4 sine squared theta times, close bracket, 2 cos theta. Lower limit 0, upper limit pi over 6. So multiply 2 cos theta across. So now here we have 2 root 3 cosine theta minus 2 times the 2 here after getting the square root of 4, then it becomes now 4 cos squared theta. And so the next step here is now we have 2 over 3 cos theta, 4 cos theta as our integrand. And we can now convert cos squared theta into cos 2 theta plus 1 over 2. And that means that the integrand now becomes 2 root 3 cos theta minus 4 divided by 2 is 2. So 2 times cos 2 theta plus 1. And so now integrating this, we have 2 over 3 sine theta minus, since we have twice cos 2 theta, the integral of that becomes sine 2 theta. And then this 2 times 1, so the integral of 2 is 2 theta. And so now we can substitute the upper limit and the lower limit to this. So we have 2 root 3 sine pi over 6 minus 2 sine 2 pi over 6 minus 2 pi over 6 minus 2 root 3 sine 0 minus sine 0 minus 0. So this entire lower limit, this lower component becomes 0. So sine pi over 6 is the same as a half. So half times 2, this becomes root 3. And then sine 2 times pi over 6, that is sine of pi over 3, becomes root 3 over 2. And then 2 times pi over 6 is pi over 3. And so root 3 minus root 3 over 2 is the same as root 3 over 2 minus pi over 3. So this is the answer from the green integral. So our initial integral consisting of these two subparts is the same as the blue minus the green component. And we know the blue could be bunched as twice the integral of the same integrand from 0 to 1. And the same applied to the green. So 2 times 2 pi over 3 minus root 3 over 2. This is what we found for this blue integral. Minus 2, the value of the green integral was root 3 over 2 minus pi over 3. We can factor 2 out, and then we have now 2 pi over 3 minus pi over 3. So this is the same as 2 pi over 3 plus pi over 3, which becomes pi. And then minus root 3 minus root 3 over 2. So this is root 3. So we have now 2 times pi minus root 3. And the answer being 2 pi minus 2 root 3. And this is the answer to our problem. I hope you did enjoy following along. Certainly, it was an absolute pleasure to be able to solve this problem and share it with you. Until next time, adios.